Welcome to Tech with Kaushik. This is set 3 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 3. Question number 40. This one focuses on troubleshooting. Scenario. An application runs on an Amazon EC2 auto-scaling group behind an application load balancer, ALB. Occasionally, instances fail the ALB health checks and are automatically terminated and replaced by the auto-scaling group. The development team needs to analyze the application logs from the failed instances to determine the root cause, but the instances are currently being terminated and deleted before the developers can access the logs. How can a DevOps engineer automate the collection of these logs before the instances are destroyed? Options. Option A. Add an auto-scaling. EC2_instance_ terminating lifecycle hook to the auto-scaling group. Create an Amazon event bridge rule to capture the lifecycle action event and trigger an AWS Lambda function. Have the Lambda function use systems manager run command to upload the logs to Amazon S3 and then call complete lifecycle action. Option B. Add an auto-scaling. EC2_instance_ terminating lifecycle hook to the auto-scaling group. Create an AWS config rule to detect the terminating state and trigger an AWS step function state machine that pushes the logs to S3 and then terminates the instance. Option C. Add an auto-scaling. EC2_instance_ launching lifecycle hook to the auto-scaling group to place the instance in a pending wait state. Create a CloudWatch alarm on the EC2 instance terminate successful metric to trigger log collection. Option D. Modify the auto-scaling group termination policy to oldest instance. Enable termination protection on all instances. Trigger an AWS Lambda function daily to manually collect logs and remove termination protection. In this case, choose option A. Add an auto-scaling. EC2_instance_ terminating lifecycle hook to the auto-scaling group. Create an Amazon event bridge rule to capture the lifecycle action event and trigger an AWS Lambda function. Have the Lambda function use systems manager run command to upload the logs to Amazon S3 and then call complete lifecycle action. The main reason is an auto-scaling lifecycle hook can pause an instance during its termination process by placing it in the terminating wait state. This prevents the instance from being deleted immediately. You can configure an event bridge rule to capture this lifecycle event and trigger an AWS Lambda function. The Lambda function can then programmatically execute an AWS Systems Manager run command script on the instance to package and upload the application logs to S3. Once the upload finishes, the Lambda function calls the Complete Lifecycle Action API, allowing the auto-scaling group to proceed with destroying the instance. Now let's rule out the other options. B. AWS Config is a configuration auditing service. It is not designed to trigger real-time actions based on auto-scaling lifecycle events. EventBridge is the native event routing service. C. Placing an instance in a pending wait state is for the launch lifecycle, auto-scaling. EC2_instance_ launching, not for instances that are being terminated. Furthermore, CloudWatch alarms are not the native mechanism for capturing lifecycle events. D. Modifying the termination policy and using termination protection defeats the purpose of an auto-scaling group automatically replacing unhealthy instances behind an ALB, leading to degraded availability. A helpful shortcut is this. To troubleshoot instances before an auto-scaling group deletes them, use the auto-scaling. EC2_instance_ terminating lifecycle hook. Capture the event with EventBridge to trigger a Lambda function that extracts logs, then explicitly signal complete lifecycle action. Next, question number 41. A DevOps engineer is configuring a blue/green deployment for a microservice hosted on Amazon Elastic Container Service, Amazon ECS. The deployment is orchestrated by AWS Code Deploy via AWS Code Pipeline. The business requires that during the deployment, test traffic must be routed to the new ECS task set so an automated integration test suite can verify its functionality. The scripts take approximately 3 minutes to run. If the test scripts encounter any errors, the deployment must automatically roll back. Production traffic should only be shifted to the new version if the tests pass. Which strategy will meet these requirements? Choices. Option A. In the code deploy appspec.yml file, define an after-allow test traffic hook that invokes an AWS Lambda validation function. Have the function run the integration tests and call put lifecycle event hook execution status with succeeded or failed. Configure automatic rollback for deployment failure so production traffic shifts only after a successful validation. Option B. Add an AWS code build stage to the code pipeline immediately before the code deploy stage. Run the integration tests against the source code. If the code build stage fails, the pipeline halts before code deploy begins. Option C. In the code deploy appspec.yml file, define a hook for the after-allow traffic lifecycle event to invoke the test scripts via Lambda. If errors are found, use the AWS deploy stop deployment command within the Lambda function to stop the deployment. Option D. Add an AWS Lambda action to the code pipeline between the source and deploy stages. Have the Lambda function deploy a temporary ECS task to run the tests, and fail the pipeline action if the tests fail. Go with option A. In the code deploy appspec.yml file, define an after-allow test traffic hook that invokes an AWS Lambda validation function. Have the function run the integration tests and call put lifecycle event hook execution status with succeeded or failed. Configure automatic rollback for deployment failure so production traffic shifts only after a successful validation. For an Amazon ECS blue/green deployment, after-allow test traffic runs after test traffic reaches the replacement task set and before production traffic is allowed. A Lambda validation hook reports succeeded or failed to code deploy with put lifecycle event hook execution status. Reporting failed causes the deployment to fail, and automatic rollback can return traffic to the original task set. B. A pre-deployment code build stage cannot validate the actual replacement task set receiving test traffic. C. After-allow traffic occurs after production traffic has already been shifted, which violates the requirement. D. Testing a separately created temporary task does not validate the replacement task set that code deploy is about to promote. The main takeaway is for ECS blue/green validation, use after-allow test traffic to test the replacement task set and explicitly report the hook result to code deploy before production traffic shifts. Here comes question number 42. We're moving on to infrastructure as code. Here's what is happening. An enterprise wants to empower developers to self-provision infrastructure using AWS CloudFormation. However, the security team requires strict governance. Developers must only deploy pre-approved templates. Resources must enforce specific tagging standards, like cost center and environment, and deployments must be restricted to a single approved AWS region. The developers must not be granted broad IAM permissions that would allow them to bypass these rules or create arbitrary infrastructure. Which solution ensures resources are deployed strictly in accordance with company policy? Review the options. Option A. Create AWS Trusted Advisor checks to find and remediate any CloudFormation stacks that lack the required tags or are deployed in unapproved regions. Option B. Enable AWS CloudFormation drift detection on all developer stacks to identify unapproved resource changes and trigger an AWS Lambda function for remediation. Option C. Implement AWS CloudFormation stack sets with the approved templates and deploy them to the developer's accounts from a central management account. Option D. Use AWS Service Catalog. Create portfolios containing products based on the approved CloudFormation templates. Apply template constraints and tag options, and grant developers permissions to launch the products. The right response is option D. Use AWS Service Catalog. Create portfolios containing products based on the approved CloudFormation templates. Apply template constraints and tag options, and grant developers permissions to launch the products. This works because AWS Service Catalog allows organizations to create and manage catalogs of IT services that are approved for use on AWS. By wrapping approved CloudFormation templates into Service Catalog products, administrators can apply strict governance constraints. Template constraints can restrict parameters, like allowed regions or EC2 instance types, and tag options force users to apply specific tags during provisioning. Users are granted permissions to interact with Service Catalog, which then assumes a secure launch role to provision the resources on their behalf, strictly enforcing the principle of least privilege. Here's why the alternatives are not suitable. A. AWS Trusted Advisor provides best practice recommendations for cost optimization, security, and performance. It does not actively prevent or remediate non-compliant CloudFormation stack deployments. B. CloudFormation drift detection identifies when resources have been modified manually outside of CloudFormation. It does not prevent developers from deploying unapproved templates in the first place. C. CloudFormation stack sets are designed for administrators to deploy identical infrastructure across multiple accounts and regions simultaneously. They are not a self-service portal for developers to provision resources on demand with tagging constraints. Whenever a scenario requires developers to self-provision infrastructure from approved templates while enforcing strict tagging, region constraints, and least privilege, AWS Service Catalog is the required solution. Question number 43. Let's go. A company is establishing a multi-account environment in AWS organizations. A DevOps engineer must deploy AWS config and AWS CloudTrail to all existing and future member accounts as a baseline security control. Local account administrators must be able to view these services and create their own custom AWS config rules or local CloudTrail trails. However, the local administrators must be explicitly blocked from modifying or disabling the centrally deployed baseline configurations. Which solution will meet these requirements in the most operationally efficient way? Option A. Deploy the baseline with an AWS CloudFormation stack set that uses service-managed permissions, targets the required organizational units, OUs, and enables automatic deployment for new accounts. Apply an SCP to member accounts that denies update, stop, and delete operations on the centrally managed CloudTrail trail, and denies reconfiguration, stopping, or deletion of the AWS config recorder for local principals, while exempting the stack set's execution role by using an AWS principal ARN condition. Option B. Enroll the existing accounts in AWS Control Tower. Grant the individual account administrators broad IAM policies that allow access to CloudTrail and AWS config, but use permission boundaries to deny deletion of the specific baseline resource ARNs. Option C. Designate an AWS config management account. Create an AWS CloudFormation template that defines the standard account resources. Deploy the template using stack sets with the stack policy set to deny update, delete actions. Option D. Create an AWS Lambda function triggered by AWS CloudTrail events that detects if a user attempts to delete a baseline AWS config rule or trail. Have the Lambda function immediately recreate the resource and revoke the user's IAM permissions. The best choice is Option A. Deploy the baseline with an AWS CloudFormation stack set that uses service-managed permissions, targets the required organizational units, OUs, and enables automatic deployment for new accounts. Apply an SCP to member accounts that denies update, stop, and delete operations on the centrally managed CloudTrail trail, and denies reconfiguration, stopping, or deletion of the AWS config recorder for local principals, while exempting the stack set's execution role by using an AWS principal ARN condition. This is the best choice because service-managed stack sets can deploy the baseline to existing accounts and automatically add stack instances as accounts join targeted OUs. An SCP is an organization-level guardrail that member account administrators cannot bypass. Scoping the CloudTrail deny to the central trail, protecting the config recorder, and exempting the stack set's execution role lets central automation maintain the baseline, while local administrators can still create unrelated trails and config rules. The other choices do not work because B. Permissions boundaries apply to IAM principles and do not provide an organization-level, centrally enforced guardrail against every local administrator. C. A CloudFormation stack policy protects updates performed through CloudFormation. It does not block direct service API calls against deployed resources. D. Detecting and recreating deleted resources is reactive and permits a period in which the baseline is disabled. Keep this point in mind for the exam. For centrally managed multi-account baselines, combine automatic service-managed stack sets deployment with SCP guardrails. Protect only the baseline controls so member accounts can still create approved local resources. Now for question number 44. The focus now shifts to multi-account automation. Here's the scenario. A company has AWS config enabled in all of its current AWS accounts. The company anticipates creating hundreds of new AWS accounts within AWS organizations over the next year, utilizing multiple organizational units, OUs. A DevOps engineer needs to ensure that AWS config is automatically enabled and configured with the company's baseline recording rules in every new account as soon as it is provisioned. Which solution will meet this requirement with the least manual intervention? The choices are: Choice A. From the organization's management account, create an AWS CloudFormation stack set containing the AWS config baseline resources. Configure the stack set to use service-managed permissions and enable automatic deployment to the organization. Choice B. In the organization's management account, create an Amazon Event Bridge rule that reacts to a Create Account API call. Configure the rule to invoke an AWS Lambda function that assumes a role in the new account and enables AWS config. Choice C. Create a service control policy, SCP, that mandates the config. Put configuration recorder action. Apply the SCP to the root level OU to force new accounts to enable AWS config upon creation. Choice D. In the organization's management account, create an Amazon Event Bridge rule that reacts to a Create Account API call. Configure the rule to invoke an AWS Systems Manager automation runbook that enables AWS config across the organization. The answer here is option A. From the organization's management account, create an AWS CloudFormation stack set containing the AWS config baseline resources. Configure the stack set to use service-managed permissions and enable automatic deployment to the organization. Let's look at the reasoning. AWS CloudFormation stack sets with service-managed permissions are deeply integrated with AWS organizations. When you enable the automatic deployment feature on a stack set targeted at the organization root or specific OUs, AWS automatically detects when a new member account is created or moved into the target scope. It then automatically provisions the CloudFormation stack, enabling AWS config in this scenario in the new account without any custom scripting, event bridge rules, or Lambda functions. The remaining options can be eliminated because B. Using Event Bridge and Lambda to assume cross-account roles and run scripts is unnecessary operational overhead, as stack sets with automatic deployment natively handles account lifecycle events. C. Service control policies, SCPs, define the maximum available permissions. They do not provision resources, create configuration recorders, or execute API calls to turn services on. D. Event Bridge triggering systems manager automation requires maintaining custom runbooks and cross-account IAM roles, whereas stack sets auto-deployment handles this natively and declaratively. Here's a useful exam tip. To automatically deploy infrastructure or security baselines, like AWS config or IAM roles, to new AWS accounts within an organization upon creation, use AWS CloudFormation stack sets configured with service-managed permissions and automatic deployment. Next up is question number 45. A development team needs to deploy infrastructure using AWS CloudFormation. To adhere to the principle of least privilege, the developer's IAM role does not possess the extensive permissions required to create the underlying resources defined in the templates, such as IAM roles, VPCs, and databases. The DevOps engineer must provide a secure way for the developers to successfully deploy the CloudFormation stacks without granting them broad administrative permissions directly. Which solution will meet these requirements? Here are the options. Option A. Create a dedicated IAM service role for AWS CloudFormation containing the extensive permissions required to provision the resources. Attach an IAM policy to the developer's role granting the IAM pass role permission for this service role, allowing them to pass it to CloudFormation during stack creation. Option B. Create an IAM policy that allows full access to AWS CloudFormation. Attach the policy to the developer IAM role so they can provision the required resources through the CloudFormation console. Option C. Create an IAM permissions boundary that encapsulates the extensive permissions required for the resources. Attach the boundary directly to the developer's IAM role. Option D. Create an AWS CloudFormation service role that has the required permissions. Grant the developer IAM role a CloudFormation * action. Instruct the developers to assume the service role locally using the AWS CLI before executing deployments. Go with option A. Create a dedicated IAM service role for AWS CloudFormation containing the extensive permissions required to provision the resources. Attach an IAM policy to the developer's role granting the IAM pass role permission for this service role, allowing them to pass it to CloudFormation during stack creation. Here's why. AWS CloudFormation can assume a service role during stack operations. This allows you to separate the permissions required to manage stacks from the permissions required to create the underlying AWS resources. By creating a CloudFormation service role with broad permissions, developers do not need those permissions themselves. Instead, you grant the developers the IAM pass role permission specifically for that service role. During deployment, the developers pass the role to CloudFormation, which assumes the role and creates the infrastructure, strictly maintaining least privilege for the human users. Let's quickly check the incorrect choices. B. Granting developers full access to CloudFormation does not give them the permissions to create the underlying resources, VPCs, DBs, etc. They would still hit access denied errors unless they are given admin access, violating least privilege. C. A permissions boundary limits the maximum permissions a role can have. It does not grant permissions. If the developer's role lacks permissions, adding a boundary will not solve the issue. D. Developers cannot assume an AWS service role locally using the AWS CLI. Service roles have trust policies specifically allowing AWS services, like CloudFormation.AmazonAWS.com, to assume them, not human IAM identities. Exam tip. To allow users with limited permissions to deploy extensive infrastructure via CloudFormation, create a CloudFormation service role with the necessary permissions and grant the user's IAM pass role to pass that role to the CloudFormation stack. Next, question number 46. Scenario. A media company hosts static video files in an Amazon S3 bucket. Following a marketing campaign, bandwidth usage has spiked dramatically. The operations team needs to determine which specific video files are being downloaded the most, how many unique users are accessing them, and the IP addresses originating the requests. The team needs a solution to query this information that requires the least amount of setup and ongoing infrastructure management. How should the company meet these requirements? Option A. Enable Amazon S3 server access logging to write logs to a dedicated S3 bucket. Create an external table in Amazon Athena pointing to the log bucket, and use standard SQL queries to aggregate and analyze the access patterns. Option B. Configure Amazon S3 event notifications to invoke an AWS Lambda function for every S3 GetObject event. Configure the Lambda function to write the access metadata to an Amazon Aurora database. Query the Aurora database to analyze the patterns. Option C. Enable AWS CloudTrail data events for the S3 bucket. Send the CloudTrail events to Amazon CloudWatch logs. Stream the matching events into Amazon OpenSearch service, and use OpenSearch queries and dashboards to analyze object access. Option D. Enable Amazon S3 server access logging. Import the access logs continuously into an Amazon RDS for PostgreSQL database using AWS Database Migration Service, AWS DMS. Use SQL queries to analyze the patterns. In this case, choose option A. Enable Amazon S3 server access logging to write logs to a dedicated S3 bucket. Create an external table in Amazon Athena pointing to the log bucket, and use standard SQL queries to aggregate and analyze the access patterns. The main reason is S3 server access logs record request details that include the object key, requester information, and remote IP address. Athena can query those log objects directly in Amazon S3 with SQL and is serverless, so the pattern supports ad hoc aggregation of downloads and source addresses without provisioning a database or search cluster. Now let's rule out the other options. B. Amazon S3 event notifications do not provide notifications for GetObject requests, so this design cannot capture every download as stated. C. CloudTrail data events can record S3 object access, but adding log streaming and OpenSearch introduces more setup and ongoing service overhead than S3 access logs with Athena. D. Loading logs continuously into our DS with DMS adds database infrastructure and ingestion complexity that the serverless Athena design avoids. A helpful shortcut is this. For low operations analysis of S3 request logs, store logs in S3 and query them in place with Athena instead of building a persistent database or search cluster ingestion pipeline. Question number 47. Let's go. Next, let's move into data protection. A DevOps engineer must configure Amazon S3 cross-region replication, CRR, to back up critical compliance data. The data originates in a source bucket in US, East, one owned by account A, and must be replicated to a destination bucket in US, West, two owned by account B. Both S3 buckets have private bucket policies and block public access. Versioning is already enabled on both the source and destination buckets. Which combination of steps is required to successfully enable and authorize this cross-account replication? Choose 3. Choose every option that satisfies the requirement. Choices. Option A. Create an IAM role in account A, the source account, with permissions to read from the source bucket and replicate objects to the destination bucket. Option B. Create a replication rule on the source bucket in account A specifying the destination bucket and attaching the replication IAM role. Option C. Update the bucket policy on the destination bucket in account B to explicitly allow the replication IAM role from account A to perform S3 replicate object actions. Option D. Create an IAM role in account B, the target account, with permissions to pull objects from the source bucket in account A. E. Create a replication rule on the target bucket in account B to actively pull objects from the source bucket in account A. F. Update the bucket policy on the source bucket in account A to allow account B to read the objects using the S3 get object action. You should choose option A. Create an IAM role in account A, the source account, with permissions to read from the source bucket and replicate objects to the destination bucket. Option B. Create a replication rule on the source bucket in account A specifying the destination bucket and attaching the replication IAM role. And option C. Update the bucket policy on the destination bucket in account B to explicitly allow the replication IAM role from account A to perform S3 replicate object actions. S3 replication requires versioning on both buckets. The scenario states that prerequisite is already satisfied. Account A provides the IAM replication role and the replication rule on the source bucket. Because the destination bucket belongs to account B, its bucket policy must authorize the source account replication role to write replicas. Together, A, B, and C implement the native cross-account replication model. D. S3 replication uses a role in the source account. The destination does not pull objects with its own role. E. Replication rules are configured on the source bucket, not as pull rules on the destination. F. Account B does not need direct GetObject permission on the source bucket because Amazon S3 assumes the source replication role to read and replicate the objects. The main takeaway is for S3 cross-account replication, enable versioning on both buckets, configure the replication rule and role on the source, and authorize that source role in the destination bucket policy. Question number 48. Scenario. A web application runs on Amazon EC2 instances within an auto-scaling group behind an application load balancer. A DevOps engineer is configuring a blue/green deployment pipeline using AWS Code Deploy. The business requirements mandate that during a deployment, a completely new replacement fleet of instances must be launched and verified. Once traffic is fully shifted to the new fleet, the original instances must be kept running for exactly 1 hour to allow for rapid rollback if unexpected errors occur. After 1 hour, the original instances must be automatically terminated to save costs. Which solution will satisfy these requirements? Options. Option A. Configure an AWS Code Deploy blue/green deployment group. Specify the auto-scaling group as the target. Select the option to reroute traffic immediately and configure the deployment group to terminate the original instances after a waiting period of 1 hour. Option B. Use AWS CloudFormation to create a new auto-scaling group alongside the old one. Set a deletion policy of 1 hour on the original auto-scaling group resource. Update the stack to shift traffic via the application load balancer. Option C. Deploy the application using 2 AWS Elastic Beanstalk environments. Perform a name swap to shift traffic. Configure an Elastic Beanstalk application version lifecycle policy to terminate the original environment after 1 hour. Option D. Configure an AWS Code Deploy in-place deployment group. Add a hook in the appspec.yml file to launch new instances via the AWS CLI, shift traffic, and run a sleep 3600 command before terminating the old instances. The answer here is option A. Configure an AWS code deploy blue/green deployment group. Specify the auto-scaling group as the target. Select the option to reroute traffic immediately and configure the deployment group to terminate the original instances after a waiting period of 1 hour. This works because AWS Code Deploy provides native support for blue/green deployments on Amazon EC2 instances managed by an auto-scaling group. When configuring a blue/green deployment group, you can specify exactly how and when traffic is shifted. Furthermore, Code Deploy allows you to configure the lifecycle of the original blue instances. You can choose to keep the original instances running for a specified waiting period, for example, 1 hour, before Code Deploy automatically terminates them. This perfectly satisfies the requirement for a rapid rollback window without requiring custom scripting. Here's why the alternatives are not suitable. B. Cloud formation deletion policy prevents a resource from being deleted when the stack is deleted. It does not set a timer to delete a resource after 1 hour. C. Elastic Beanstalk allows you to swap environment names, but terminating the original environment automatically after a precise 1-hour wait requires custom lifecycle rules or manual intervention, which is not as native as Code Deploy's built-in wait timer. D. An in-place deployment group replaces the application on the existing instances. It does not launch a completely new replacement fleet. Pausing a deployment with Sleep 3600 inside a hook ties up the deployment pipeline and blocks further operations. AWS Code Deploy blue/green deployments for EC2 natively support a feature to keep the original blue auto-scaling group instances running for a defined wait time, up to days, before automatically terminating them. Question number 49. This question takes us into disaster recovery. A mission-critical application runs on Amazon EC2 instances in auto-scaling groups in the US East 1 region. To prepare for disaster recovery, the company deploys a warm standby environment in the EU West 1 region. Session data must be replicated between regions in near real time. The architecture must automatically route all traffic to the standby region if the primary region experiences a widespread failure. Additionally, the operations team wants approximately 1% of standard production traffic over time to be continuously routed to the standby region to verify its health and readiness. Both regions are configured to scale automatically based on load. How should a DevOps engineer meet these routing and data replication requirements? Options. Option A. Use Amazon DynamoDB global tables to replicate session data between the regions. Use an Amazon Route 53 weighted routing policy with Route 53 health checks. Assign a weight of 99 to the primary region and 1 to the standby region. Option B. Use Amazon RDS for MySQL with cross-region read replicas for session data. Use an Amazon Route 53 failover routing policy with health checks to distribute the traffic across the regions, prioritizing the primary. Option C. Use Amazon DynamoDB regional tables and AWS Database Migration Service, AWS DMS, to replicate session data. Deploy an Amazon CloudFront distribution and use CloudFront functions to randomly route 1% of requests to the European origin. Option D. Use Amazon Elastic Cache for RedISS Global Data Store for session data. Configure an AWS Global Accelerator Standard Accelerator with endpoint weights of 99 for us, East 1 and 1 for you, West 1, relying on standard TCP health checks. The right response is option A. Use Amazon DynamoDB global tables to replicate session data between the regions. Use an Amazon Route 53 weighted routing policy with Route 53 health checks. Assign a weight of 99 to the primary region and 1 to the standby region. This is the best choice because DynamoDB global tables provide multi-region replication for the session data. Route 53 weighted records with weights 99 and 1 return healthy endpoints in approximately that proportion over time while both regions are healthy. When health checking marks the primary record unhealthy, Route 53 stops selecting that record, so DNS responses are directed to the healthy standby. The other choices do not work because B. Route 53 failover routing prioritizes the primary and does not continuously send a small percentage of normal traffic to the secondary. C. Regional DynamoDB tables with DMS and custom CloudFront routing add unnecessary components compared with native global tables and Route 53. D. Elastic Cache Global Data Store does not provide the same active multi-region write model for session data, making normal application traffic to the secondary region problematic. Keep this point in mind for the exam. Route 53 weighted routing provides proportional traffic distribution over DNS responses, not an exact per-request percentage. Combine weights with health checks when weighted testing must also fail over. Question number 50. Let's go. Scenario. A continuous delivery pipeline in AWS code pipeline deploys a web application. The pipeline consists of the following stages. AWS code build compiles the artifact and runs unit tests. AWS code deploy deploys the application to a staging environment. AWS code deploy deploys the application to a production environment. The security team requests that before the production deployment begins, the pipeline must pause. During this pause, an automated penetration testing suite hosted on an internal REST API must be executed against the staging environment. The security team will review the API test results offline and explicitly approve the pipeline to proceed to production. Which combination of actions should the DevOps engineer take to fulfill this request? Choose two. More than one answer may be correct. Choices. Option A. Add an AWS Lambda action to the pipeline immediately following the staging deployment to invoke the penetration testing REST API. Option B. Add a manual approval action to the pipeline immediately following the Lambda action, requiring the security team to review the test results before the production stage begins. Option C. Update the code deploy deployment group for the production environment to mandate a manual approval step within the code deploy console. Option D. Modify the code build spec.yml file to execute the REST API via curl and wait indefinitely for a callback response from the security team. E. Add a manual approval action between the source stage and the build stage to ensure the security team approves the code before testing begins. The answers that work here are Option A. Add an AWS Lambda action to the pipeline immediately following the staging deployment to invoke the penetration testing REST API, and Option B. Add a manual approval action to the pipeline immediately following the Lambda action, requiring the security team to review the test results before the production stage begins. Let's look at the reasoning. AWS code pipeline supports native integration with AWS Lambda. By adding a Lambda action after the staging deployment stage, the pipeline can programmatically invoke the internal REST API to trigger the penetration testing suite. A. Immediately following the Lambda action, a manual approval action can be inserted into the pipeline. This explicitly pauses the pipeline execution, allowing the security team time to review the test results generated by the API offline. The deployment to production will only proceed once an authorized user explicitly approves the action in the console. B. The remaining options can be eliminated because C. While code deploy supports deployment approvals, keeping the pipeline orchestration logic, approval gates, within code pipeline provides a centralized, unified view of the release process and is the best practice for CI/CD flow control. D. Having code build curl an API and wait indefinitely for a callback consumes build minutes needlessly and risks timing out the code build execution environment, which has a maximum timeout of 8 hours. E. A manual approval before the build stage stops the pipeline before the code is even compiled or tested, meaning the security team would have no artifact or staging environment to review. Here's a useful exam tip. To integrate external automated tools like APIs or custom scripts into AWS code pipeline, use AWS Lambda actions. To pause a pipeline for human review or offline testing, use a manual approval action. Next, question number 51. We're moving on to CloudWatch logs. Scenario. A company suspects a specific list of known malicious IP addresses is attempting to access a critical internal application hosted in a production VPC. The application is experiencing heavy, legitimate usage. The security team wants an immediate, automated notification if any IP address from their deny list successfully establishes a connection, accepted traffic, with the application. The product manager insists the solution must be highly cost-effective and avoid expensive continuous querying or dedicated search clusters. Which solution meets these requirements most cost-effectively? Option A. Enable VPC flow logs for the VPC and route the logs to Amazon CloudWatch logs. Create a CloudWatch logs metric filter that uses a filter pattern to match the specific deny list IP addresses in the accept action. Create a CloudWatch alarm based on this metric that publishes to an Amazon SNS topic. Option B. Enable VPC flow logs and route them to an Amazon S3 bucket. Configure Amazon Athena to query the bucket continuously for the IP addresses. Use Amazon QuickSight to trigger a threshold alert when an IP matches, sending an email to the security team. Option C. Enable VPC flow logs and route them to an Amazon S3 bucket. Configure an Amazon OpenSearch service domain. Use an AWS Lambda function triggered on a schedule to ingest the S3 logs into OpenSearch and use OpenSearch alerting to notify the team via SNS. Option D. Enable VPC flow logs and route them to Amazon CloudWatch logs. Deploy an Amazon Athena CloudWatch connector via AWS Lambda. Schedule an event bridge rule every 5 minutes to query the logs via Athena and publish findings to SNS. The best choice is option A. Enable VPC flow logs for the VPC and route the logs to Amazon CloudWatch logs. Create a CloudWatch logs metric filter that uses a filter pattern to match the specific deny list IP addresses in the accept action. Create a CloudWatch alarm based on this metric that publishes to an Amazon SNS topic. Here's why. VPC flow logs capture IP traffic information. By routing them to Amazon CloudWatch logs, you can utilize CloudWatch metric filters. A metric filter parses incoming log data in near real time for specific patterns, like a list of IPs and the word accept, and increments a CloudWatch metric. You then attach a CloudWatch alarm to this metric to trigger an SNS notification. This architecture is entirely serverless, operates continuously in near real time, and is highly cost-effective because metric filters cost nothing extra beyond standard CloudWatch logs ingestion rates. Let's quickly check the incorrect choices. B. Amazon Athena charges per query based on data scanned. Running continuous queries against high-volume VPC flow logs to achieve near real-time alerting is extremely expensive and inefficient. C. Amazon OpenSearch service requires provisioning a cluster of EC2 instances, which introduces a high, fixed baseline cost and ongoing maintenance, violating the product manager's strict cost-effectiveness constraint. D. Deploying a Lambda function to continuously query Athena on a 5-minute schedule will accrue significant Lambda and Athena scanning costs over time compared to native CloudWatch metric filters. Exam tip. For near real-time, cost-effective alerting on specific text patterns, like IP addresses, error strings, or HTTP status codes, within logs, route the logs to CloudWatch logs and use metric filters linked to CloudWatch alarms. Question number 52. Let's go. A financial organization uses AWS organizations to manage multiple AWS accounts. A strict information security policy dictates that any Amazon EBS volume provisioned without encryption must be flagged as non-compliant. The DevOps team must ensure this compliance check is deployed uniformly across all existing and future accounts automatically, and local account administrators must be explicitly prevented from disabling the check. Which solution will accomplish this? Options. Option A. Use AWS Systems Manager Quick Setup to deploy and maintain an AWS configuration recorder across the entire organization and required regions. From the AWS config delegated administrator, deploy an organization managed rule using encrypted _volumes. Attach an SCP that prevents local principals from reconfiguring, stopping, or deleting the configuration recorder while exempting the central quick setup or stack sets automation role. Option B. Enable Amazon Inspector centrally for all member accounts and use Amazon Event Bridge to aggregate inspector findings that are related to Amazon EBS volumes. Option C. Create a service control policy, SCP, in organizations that denies the EC2. Create volume action if the EC2 encrypted condition is false. Use Amazon Athena to analyze AWS CloudTrail logs for access denied events. Option D. Create an IAM role in a central security account. Build an AWS code pipeline that invokes an AWS Lambda function to assume the role in every member account. List all EBS volumes and publish a compliance report to Amazon S3. The best choice is option A. Use AWS Systems Manager Quick Setup to deploy and maintain an AWS configuration recorder across the entire organization and required regions. From the AWS config delegated administrator, deploy an organization managed rule using encrypted _volumes. Attach an SCP that prevents local principals from reconfiguring, stopping, or deleting the configuration recorder while exempting the central quick setup or stack sets automation role. The main reason is AWS config organization rules can be centrally deployed to member accounts, but evaluations require an available configuration recorder. Systems Manager Quick Setup can deploy and maintain config recording across an organization and regions. The encrypted_volumes managed rule flags unencrypted EBS volumes, and the SCP prevents local administrators from reconfiguring, stopping, or deleting the recorder while the central automation path remains exempt. Now let's rule out the other options. B. Current Amazon Inspector is a vulnerability management service and does not evaluate EBS encryption as an AWS config compliance rule. C. Denying unencrypted volume creation is preventive, but it does not provide the required config-style non-compliance evaluation for existing or otherwise discovered volumes. D. A custom pipeline that inventories accounts is more operationally complex and does not provide the native organization-wide config compliance control. A helpful shortcut is this. For organization-wide config compliance, ensure recorders exist in every target account and region, deploy an organization rule centrally, and use SCPs to prevent member account principals from disabling the recording path. Next, question number 53. A company provides a public REST API using Amazon API Gateway and backend AWS Lambda functions. The application data is stored in Amazon DynamoDB. The user base is evenly split between North America and Europe. The company requires a globally distributed architecture that minimizes network latency for all users, while keeping the database state synchronized across both continents in near real time. Which solution will meet these latency and reliability requirements? Option A. Deploy the API Gateway and Lambda functions in both a North American and a European AWS region. Configure the Lambda functions to read and write to an Amazon DynamoDB global table spanning both regions. Use an Amazon Route 53 latency-based routing policy to direct users to the API Gateway in the region nearest to them. Option B. Deploy the API Gateway and Lambda functions in both a North American and a European AWS region. Configure the Lambda functions to write to regional DynamoDB tables. Use AWS Database Migration Service, AWS DMS, to continuously replicate data between the two regional tables. Option C. Deploy the API Gateway in North America and configure it to proxy requests to Lambda functions in both North America and Europe. Configure the Lambda functions to access a single DynamoDB table located in North America. Option D. Configure Amazon Route 53 with a geolocation routing policy pointing to a single API gateway in North America. Use Amazon CloudFront to cache the DynamoDB database responses at the edge locations in Europe to reduce latency. Go with Option A. Deploy the API Gateway and Lambda functions in both a North American and a European AWS region. Configure the Lambda functions to read and write to an Amazon DynamoDB global table spanning both regions. Use an Amazon Route 53 latency-based routing policy to direct users to the API Gateway in the region nearest to them. To minimize network latency for globally distributed users, the compute tier, API Gateway, and Lambda must be deployed in multiple regions closest to the users. Amazon Route 53 latency-based routing automatically directs users to the region that provides the lowest network latency. For the database tier, Amazon DynamoDB global tables provide fully managed, active-active, multi-region replication. The regional Lambda functions read and write to their local DynamoDB replica, ensuring sub-millisecond database latency, while DynamoDB asynchronously synchronizes the state across continents in near real time. B. Using AWS Database Migration Service, DMS, for continuous active-active bidirectional replication between DynamoDB tables is an unscalable, complex anti-pattern. DynamoDB Global Tables handles this natively and seamlessly. C. If Lambda functions in Europe access a DynamoDB table in North America, they suffer transatlantic cross-region latency on every database call, defeating the purpose of global distribution. D. While CloudFront accelerates content delivery, it caches responses based on standard HTTP caching headers, TTL. It cannot act as a synchronized database replica for backend Lambda functions that need to write data or query unpredictable states. The main takeaway is the standard AWS serverless pattern for globally distributed active-active applications is Route 53 latency routing leads to regional API gateway, leads to regional Lambda, leads to DynamoDB global tables. Question number 54. Next, let's move into disaster recovery. Scenario. A company uses a single Amazon Aurora MySQL database cluster to store both its global product catalog and its customer order data in the US East 1 region. The company is expanding operations to Europe. To comply with data residency laws, European customer orders must be stored strictly in a European AWS region. However, the product catalog is identical globally, read-heavy, and needs to be highly available with low latency in both regions. The development team wants to accomplish this with the least amount of application refactoring and must continue using SQL. How should the company architect the database layer? Choices. Option A. Migrate the product catalog tables to an Amazon Aurora global database, with the primary cluster in US East 1 and a read-only secondary cluster in the European region. Provision separate, standalone regional Amazon Aurora database clusters in each region specifically for the customer order data. Option B. Migrate the product catalog and customer orders to Amazon DynamoDB global tables. Modify the application to use NoSQL query patterns. Keep the European customer order data in the European regional table replica. Option C. Use Amazon Redshift for the product catalog to allow cross-region querying. Migrate the customer order data to Amazon DynamoDB regional tables to ensure data residency compliance in each region. Option D. Keep all data in the existing Amazon Aurora MySQL database cluster in US East 1. Deploy AWS Database Migration Service, AWS DMS, to continuously filter and replicate only the European customer data to a new Aurora cluster in Europe. In this case, choose option A. Migrate the product catalog tables to an Amazon Aurora global database, with the primary cluster in US East 1 and a read-only secondary cluster in the European region. Provision separate, standalone regional Amazon Aurora database clusters in each region specifically for the customer order data. This works because an Amazon Aurora global database is designed for globally distributed applications, allowing a single primary database to replicate data to multiple secondary regions with sub-second latency. This perfectly satisfies the highly available, low-latency requirement for the shared product catalog while minimizing application refactoring, as it remains a MySQL-compatible SQL database. Because customer order data has strict data residency requirements, it cannot be globally replicated. Provisioning separate, standalone Aurora clusters in each respective region ensures customer data never crosses borders, completely satisfying compliance without requiring a rewrite to NoSQL. Here's why the alternatives are not suitable. B. Migrating relational SQL order data to Amazon DynamoDB requires massive application refactoring to adapt to NoSQL single-table design paradigms, violating the least amount of application refactoring requirement. C. Amazon Redshift is an OLAP data warehouse designed for massive analytical queries, not for serving high concurrency, low-latency read traffic for a live web application catalog. D. Filtering and replicating specific subsets of data, customer orders, using AWS DMS introduces significant operational complexity, replication lag, and ongoing maintenance compared to logically separating the databases at the application level. Amazon Aurora Global Database replicates the entire cluster to secondary regions. If you have strict data residency compliance requirements for a subset of data, like PI, you must separate that data into its own regional database cluster before using global database. Next, question number 55. An enterprise uses AWS Control Tower to manage a multi-account environment. A DevOps engineer wants to implement a GitOps workflow to apply custom security baselines automatically to any new AWS account provisioned via the Control Tower account factory. The baselines consist of custom AWS CloudFormation templates defining IAM roles and VPC configurations, as well as custom service control policies, SCPs, applying specific compliance rules based on the organization unit, OU. Which solution will deploy these resources and policies automatically upon account creation in the most automated way? Options. Option A. Deploy the customizations for AWS Control Tower, CFCT, solution. Configure CFCT to monitor an AWS code commit repository. Commit a manifest.yaml file, the CloudFormation templates, and the SCP-JSON documents into the repository to automatically trigger deployments to new accounts. Option B. Use AWS Service Catalog with AWS Control Tower. Create portfolios and products for the CloudFormation templates. Manually deploy the SCPs using the AWS CLI and JSON documents whenever a new account is registered. Option C. Create an Amazon Event Bridge rule to detect the Create Managed Account event. Configure the rule to trigger an AWS code build project that runs bash scripts to manually deploy the CloudFormation stacks and SCPs via the AWS CLI. Option D. Deploy AWS CloudFormation stack sets from the management account using the required templates with automatic deployment enabled. Create a secondary stack set to deploy the SCPs directly to the member accounts. The answer here is option A. Deploy the customizations for AWS Control Tower CFCT solution. Configure CFCT to monitor an AWS code commit repository. Commit a manifest.yaml file, the CloudFormation templates, and the SCP-JSON documents into the repository to automatically trigger deployments to new accounts. This is the best choice because customizations for AWS Control Tower CFCT is an AWS-provided solution designed specifically for this use case. It allows administrators to define security baselines using a GitOps workflow. By committing a manifest.yaml file, AWS CloudFormation templates, and SCP-JSON documents into a source repository, like code commit, CFCT automatically detects the changes. It integrates natively with Control Tower lifecycle events, like account factory creation, to automatically deploy the defined CloudFormation stacks and attach the SCPs to the new accounts without manual intervention. The other choices do not work because B. While Service Catalog provides governance for provisioning, it requires users to manually execute deployments via the console or CLI. It also does not natively orchestrate the deployment of service control policies, SCPs, to organizations. C. Creating custom event bridge rules triggering code build scripts to run CLI commands is a heavy custom engineering effort that duplicates the exact functionality already provided natively by the AWS CFCT solution. D. Stack sets can automate CloudFormation deployments to organizations natively, but stack sets cannot deploy service control policies, SCPs, directly. SCPs are applied via the organization's API, which CFCT handles seamlessly. Keep this point in mind for the exam. Whenever a scenario asks for a GitOps workflow to automatically deploy CloudFormation templates and service control policies, SCPs, alongside AWS Control Tower, the answer is customizations for AWS Control Tower, CFCT. Question number 56. Consider this situation. A DevOps engineer is tasked with standardizing OS patching for a hybrid environment consisting of Amazon EC2 instances running in AWS and physical servers running in an on-premises data center. The company policy dictates that patching operations must be managed from a central AWS console and executed strictly during designated non-business hours on weekends. Which combination of actions will meet these requirements? Choose 3. Identify all valid responses. Choice A. Install the AWS Systems Manager agent on the on-premises servers and register them using Systems Manager hybrid activations. Choice B. Attach an IAM instance profile containing the Amazon SSM Managed Instance Core Managed policy to the Amazon EC2 instances. Choice C. Configure AWS Systems Manager maintenance windows to define the weekend schedule and assign the patch tasks to the instances. Choice D. Run an AWS Systems Manager automation document on an hourly cron schedule to check for and install patches on all systems. Choice E. Create IAM access keys for each on-premises machine and embed them in a local script to interact with the AWS Systems Manager API. Choice F. Use Amazon Event Bridge scheduled events to trigger AWS code deploy to push the patches to the hybrid instances on weekends. The correct answers are option A. Install the AWS Systems Manager agent on the on-premises servers and register them using Systems Manager hybrid activations. Option B. Attach an IAM instance profile containing the Amazon SSM Managed Instance Core Managed policy to the Amazon EC2 instances. And option C. Configure AWS Systems Manager maintenance windows to define the weekend schedule and assign the patch tasks to the instances. Let's look at the reasoning. To centralize patching for a hybrid environment using AWS Systems Manager Patch Manager, on-premises physical or virtual servers must run the SSM agent and authenticate to AWS using Systems Manager hybrid activations, which registers them as managed instances. Amazon EC2 instances require an IAM instance profile with the Amazon SSM Managed Instance Core policy to grant the SSM agent permissions to communicate with the Systems Manager service. To ensure patches are applied strictly during non-business weekend hours, you configure AWS Systems Manager maintenance windows, specifying the cron schedule and registering the run command patch tasks targeting the fleet. The remaining options can be eliminated because running an SSM automation document hourly violates the company policy restricting patching to designated weekend non-business hours. Creating individual IAM user access keys for on-premises servers is a security anti-pattern. Systems Manager hybrid activations generate secure, temporary activation codes specifically to avoid hard-coding IAM keys. AWS Code Deploy is a deployment service for application code, not an OS patch management tool. Patching should be orchestrated via Systems Manager. Here's a useful exam tip. To manage on-premises servers alongside EC2 instances using AWS Systems Manager, install the SSM agent on-premises and authenticate using Systems Manager hybrid activations. Use maintenance windows to enforce scheduling. Question number 57. Let's go. This question takes us into deployment strategies. Scenario. A company deploys a LAMP stack application to an Amazon EC2 auto-scaling group behind an application load balancer, ALB. The legacy deployment process relies on a complex bash script executed manually from a Bastion host. The script deregisters instances from the ALB, stops the web service, updates file ownership permissions, restarts the service, and finally re-registers the instance with the ALB. The DevOps engineer must fully automate this process using native AWS Code Deploy features to replace the manual bash script entirely. Which solution achieves this natively? Choices. Option A. Create an AWS Code Deploy deployment group and specify the ALB target group within its load balancer configuration to natively handle deregistration and registration. Use the permissions section of the appspec.yml file to handle file ownership, and use the application stop and application start lifecycle hooks to run simple scripts to control the web service. Option B. Use AWS Code Pipeline to trigger AWS Code Build to test the application. Within the code build spec.yml, write AWS CLI commands to deregister and re-register the instances with the ALB. Use code deploy strictly to copy the files and restart the service. Option C. Use AWS Code Pipeline to move the application source code to AWS Code Deploy. Use code deploy's appspec.yml file to restart services and update permissions. Use an Amazon Event Bridge rule triggered by code deploy state changes to invoke a Lambda function that manages the ALB registration. Option D. Create an AWS Code Deploy deployment group. Write custom bash scripts to deregister and register the instances with the ALB via the AWS CLI. Invoke these custom scripts using the before install and after install lifecycle hooks in the appspec.yml file. The right response is Option A. Create an AWS Code Deploy deployment group and specify the ALB target group within its load balancer configuration to natively handle deregistration and registration. Use the permissions section of the appspec.yml file to handle file ownership, and use the application stop and application start lifecycle hooks to run simple scripts to control the web service. Here's why. AWS Code Deploy is designed to natively replace complex manual deployment scripts. When you configure a Code Deploy deployment group, you can specify an application load balancer target group. Code Deploy will automatically deregister instances before deployment and re-register them afterward, removing the need for custom CLI scripts. The appspec.yml file contains a dedicated permissions section to declaratively set file/folder ownership and rights on Linux systems. The application stop and application start lifecycle hooks are the designated places to run brief service control scripts. For example, system-stop HTTPD. This satisfies all requirements using built-in features. Let's quickly check the incorrect choices. B. Using code build to manually run AWS CLI commands for ALB deregistration bypasses code deploy's native integration, leading to race conditions and unnecessary complexity. C. An event bridge rule triggering a Lambda function to manage ALB registration adds disjointed external infrastructure for a feature that code deploy natively supports out of the box. D. While custom bash scripts in before install or after install could technically manage the ALB via the AWS CLI, it adds heavy scripting overhead and error handling logic that code deploy's native load balancer integration is explicitly designed to eliminate. Exam tip. AWS Code Deploy natively handles application load balancer deregistration/registration. Do not write custom AWS CLI scripts in your appspec.yml hooks to manage load balancers. Configure it directly in the deployment group settings. You have completed set 3 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.